All right, guys, we're working off the same set of notes from class yesterday, or I guess on Friday, and we're looking for how to work with some of the stuff we've been working with, and just finishing up discussing the binomial distribution. So where we left off is here with problem 2 is we want to calculate the mean and standard deviation for the quiz example. So if you remember, for a binomial distribution, distribution with n samples and the probability of a success. I guess I should write this as probability of a success is equal to p. All right, so x is a binomial distribution with all these facts. The mean of x is np, and the standard deviation of x is the square root of n times p times 1 minus p. So what do we have? If you remember, we had, for the quiz example above, there was 10 questions, and the probability of getting one right was 1 out of 5, which is 0.2. So the mean is going to be 10 times 0.2, which is 2. And if you think about it, that's what we would expect, right? If there's a 20% chance of getting something right, and there's 10 questions, we'd expect to get 2 of them right. We'd expect 20% of them to be right. And the standard deviation of x, that's the square root of 10 times 0.2 times 0.8, which is, I guess this is what? The square root of 1.6. Which, can I do that in my head? I don't know. There's our standard deviation. Okay? Now, not that bad. We have another example here. We want to suppose a batch of 10,000 flash drives, 200 effective. What is the probability that in a random selection of 10 flash drives, there are no defective flash drives? Well, we can calculate this actually 2 different ways. The first of these being, there's one correct answer and there's one approximately correct answer. The one correct answer is, in the first choice, there's 9,800 non-defective ones out of 10,000, right? And then after I select one non-defective one, there's 9,799 non-defective ones out of 9,999. And then there's 9,700. I got this wrong. There are 10,000 flash drives. Yeah, we're okay. 9,798 over 9,998. We got to do this 10 times. So this would be 9,791 out of 9,991. So that is the exact probability that there is no defective flash drives, right? Because after each time when I select one, I take it out of the pile. So what happens if I pretend that this isn't the case? In other words, what happens if I pretend that we're doing this with replacement, or that each of these events are independent, right? So here these events are dependent. Me getting a non-defective on the next step relies on me getting a non-defective on the previous step. Well, if I want to do this, I want to pretend it's a binomial distribution. This would be this would be what? So we're going to count being not defective as a success, right? So this is the I guess the probability. In 10 choices, I get 0 defectives. The probability of me getting something defective is 200 out of 10,000, right? That's the probability of getting defective, so to the 0 power, times 9,800 over 10,000 to the 10, right? So what's the difference between these two numbers? Well, I keep forgetting that 9,108, this is 8.8, 0.8171, this is 0.8170, this is 0.8171. So these are pretty close, right? They're off by 1/10,000th. Right? These are pretty close. They're off by 1/10,000th. So actually, this binomial distribution is not a bad approximation for this guy up here. And you might be saying, like, why don't we just calculate it exactly? Well, better than calculating it exactly, if this number was bigger, if it's instead of just 10, if this was 20, 30, 40, calculating this number up top would be really hard. We're calculating this number on the bottom is kind of significantly easier. And this gives us a rule, right? If a random sample of size n is taken from a population of size capital N, we can treat this random sample as a binomial random variable if, and it's the 10% rule. So one way of writing that down, we can treat it as a random variable if n divided by capital N, we treat this as a binomial if we take lowercase n divided by capital N, and this number is less than 0.1. All right? And that says essentially that, like, they're essentially the same. One is a fair approximation of the other. So for our example 3 up here, we have our population size. Our population is size 10,000. Our sample is size 10. 10 out of 10,000. That's 1 out of 1,000, so that's 0.001, which is definitely less than 0.1, right? So this is small enough where this is not a bad approximation. We can approximate this like this, all right? And then I think maybe the last and most interesting fact about the binomial distribution is that for big enough n, right? So for enough samples, our distribution becomes approximately normal. But how large is large enough? Well, I'm popping over to Desmos, and I'm going to pull up a binomial distribution. I'm going to put a slider on n. I'm going to have my probability say, it doesn't really matter what my probability is, just make it 0.7. Okay, and I'm going to put a slider on n. Right, so for n is 1, this is pretty small. The height of these points represent the probability that you have that many successes, right? So in one sample, in this case, the probability of 0 successes is 0.3. The probability of 1 success is 0.7, right? It's the height. So this is 0.3 and 0.7. But if I make my n bigger, let's say if I make my n 10, right? Here's what our distribution kind of looks like. right? And we can see that it's like it's not really symmetric, right? There's more stuff on the left than on the right, but it's starting to look kind of bell curve-ish. Now, if instead of 10, maybe we made it 50. Now, again, things get kind of spread out. I have to make this a little, play with my scale a little bit. But right, this is getting more normal distribution-y. There's always going to be a bigger tail on one side than the other. But say if I did 500, again, we gotta kind of zoom over here, but we're getting something more and more normal distribution-y, right? And that's what we're talking about with the binomial distribution. If you let your n get big enough, we start to be able to, instead of do binomial distribution calculations, we can do normal distribution calculations. And those are always the best calculations for us. They're the easiest ones to always do. But I guess the question is, how big is big enough, right? So I say when n is big enough, we can pretend it's binomial, but how big does that actually have to be? So if we take a look in the textbook, it's a 10 rule. It's the large counts conditions. It's the 10 rule. And what does that end up meaning? What we need is, how large is large enough? Well, we are approximately normal. Binomial distribution, NP, is approximately normal. If NP is greater than or equal to 10, and 1 minus p is greater than or equal to 10. You need both of these conditions satisfied, and then we are going to be approximately normal.